particle physics has long struggled with a massive discrepancy between two fundamental forces. Gravity, governed by the Planck scale, is exceptionally weak compared to the electroweak force, a gap of 16 orders of magnitude. This is the hierarchy problem. One proposed mathematical solution involves large extra dimensions. In this model, the fields of the standard model, including the active, left-handed neutrinos we observe in experiments, are strictly confined to a four-dimensional manifold known as the brane. However, the framework introduces sterile, right-handed neutrino fields. Because these fields are standard model gauge singlets, they are not trapped on the brane. They are permitted to freely propagate through a larger, higher-dimensional space called the bulk. For these particles to interact, the bulk neutrinos must connect with the active neutrinos on our brane via Euclid couplings. But because the right-handed fields are distributed across the vast volume of the extra dimensions, their wave functions on our brane are heavily diluted. This geometric dilution suppresses the interaction strength. It provides a mechanism to generate the extremely small Dirac neutrino masses we observe, without inserting artificially tiny coupling constants into the math. From our brane, a single right-handed bulk neutrino appears not as one particle, but an infinite tower of Kaluza Klein excitations. Each heavy state couples to standard active neutrinos through specific mixing elements, altering the standard three-flavor mixing matrix. The model's phenomenology depends on two specific variables: RED, the compactification radius of the dominant extra dimension, and M0, the lightest Dirac mass. When M0 is highly suppressed compared to the inverse radius of the extra dimension, the zero-mode masses look almost identical to standard neutrino masses. In this regime, only the lowest Kaluza-Klein modes are prominent enough to noticeably alter standard transition probabilities. Because these Kaluza-Klein modes inject highly specific perturbations into standard oscillation formulas, we test for string-inspired extra dimensions by searching for these precise deviations in existing neutrino data. Analytically, this dual-pane chart maps the exact physical scaling of the Kaluza-Klein masses and mixing elements against the lightest Dirac mass parameter, M0. The left pane tracks normal mass ordering, while the right pane tracks inverted ordering. Looking at the normal ordering pane on the left, the lightest mass states, M1 and M2, are significantly smaller than M3. Consequently, the dominant extra-dimensional effects emerge in the third mass state terms, which are severely suppressed by the small mixing angle UE3. The math flips for inverted ordering on the right. Here, M3 is much smaller than M1 and M2. The dominant Kaluza-Klein contributions bypass the suppression and attach directly to the first and second mass states. Unlike the third state, the mixing elements for the first and second mass states remain unsuppressed in the probability equations for electron-neutrino disappearance. Because of this mathematical asymmetry, experiments measuring beta decay and reactor antineutrinos will inherently yield significantly tighter constraints on the extra dimension if nature favors the inverted mass ordering. Historically, large extra dimensions gain traction in this field as a potential solution to the gallium anomaly. In calibration datasets from the GALAX, SAGE, and BEST experiments, researchers observed a persistent deficit in the expected ratio of electron-neutrino events. This plot maps the radius of the extra dimension against M0. The enclosed orange contour represents the exact parameter space where Kaluza-Klein oscillations neatly resolve the missing events in the gallium data. But this explanation faces an immediate hurdle when tested against data from modern short baseline reactor experiments, specifically using the precise Huber-Mueller and Ki antineutrino flux models. When we overlay the 90% confidence level exclusion lines derived from these reactor models, they slice directly through the orange contour preferred by the gallium results. Relying on a large extra dimension to explain the BEST and GALAX deficits creates a severe statistical conflict with established reactor antineutrino data. To determine which observation holds up, we must expand the global fit. We can push these parameters further by introducing high-energy, long baseline data from the MINOS and MINOS Plus accelerator experiments. MINOS operated by firing a beam of muon neutrinos, peaking between 3 and 7 giga-electronvolts, directly through the Earth's crust. The beam traveled to a detector 735 kilometers away to track the rate of particle disappearance. We combine this with a second major constraint: high statistics measurements of electron antineutrino disappearance gathered by identical detectors at the Diabé reactor experiment. Returning to our exclusion plot of the extra dimension radius versus m0, we can map the limits generated by these two datasets. The red lines represent the MINOS constraints, while the black lines denote diab at the 90 and 99% confidence levels. MINOS defines the upper boundary for the extra dimensions radius under normal mass ordering, while diab dictates a much tighter bound if we assume inverted ordering. Both of these high-precision datasets independently and thoroughly rule out the parameter space that would be required to validate the gallium anomaly. However, there is a vulnerability in these oscillation data limits. As the radius of the extra dimension gets extremely small, the exclusion bounds effectively vanish, leaving the lower edge of the graph wide open. As the extra dimension shrinks, the Kaluza-Klein modes become incredibly heavy and physically decouple from the standard neutrino interactions. The resulting probability behaves exactly like standard 3-neutrino mixing, making oscillation experiments completely blind to the M0 mass scale. This plot tracks the constraints established by the Katrin experiment, which relies on direct kinematic analysis of tritium beta decay near its spectral endpoint to measure the effective electron-neutrino mass. The orange exclusion limit descending from the top includes a small bump near 3 × 10⁻²⁰ micrometers, a statistical artifact caused by the specific spacing of the experimental data bins. For low values of the extra dimensions radius, this Katrin boundary operates as a strict vertical wall, capping the M0 mass at approximately 0.9 electron volts. Katrin's kinematic sensitivity allows us to bound the mass scale even when the extra dimensional radius is too small to trigger oscillations. It completes the exclusion map, sealing the low radius region that would otherwise remain unconstrained by oscillation physics. This final chart synthesizes all of these independent constraint axes. By layering the reactor, accelerator, and kinematic exclusion zones of diab, MINOS, and Katrin onto a single parameter space, the vast majority of the graph is blocked out. We are left with only narrow allowed regions clinging to the extreme bottom edge. Translating these allowed regions into a one-dimensional delta chi-square profile for the compactification radius gives us a definitive statistical threshold. This global fit generates absolute upper bounds on the geometry of the extra dimension, a maximum radius of 0.20 micrometers for normal ordering, and an even stricter 0.10 micrometers for inverted ordering. The results of this global fit leave no statistically viable region for a dominant extra dimension to resolve the gallium deficit. At a 90% confidence level, the model is excluded across the entire range of experimental interest. To put the power of this synthesis into perspective, we can compare these limits against traditional tabletop gravitational experiments, which test the inverse square law of gravity at microscopic scales to hunt for extra dimensions. The most precise mechanical apparatuses designed to isolate the gravitational force yield upper limits on the radius of an extra dimension at roughly 37 micrometers. By contrast, searching for the statistical ghosts of Kaluza-Klein states in oscillation data produces limits that are over 2 full orders of magnitude more precise. The most rigorous constraints we currently have on the higher dimensional geometry of spacetime are written directly into the physics of the neutrino.